We're at day 4 in the Qudrant Essentials course, and at this point, you've probably realized that when we are working with real data sets, the number of vectors that we need can grow really quickly, easily reaching millions of vectors. When we are working with high-dimensional vectors, such as embeddings from providers like OpenAI, a single 1,536-dimensional vector requires 6 kilobytes of memory. So in this scenario, with 1 million vectors, you would need around 6 gigabytes of memory to handle that. And as your dataset grows to multiple millions of vectors, the memory and processing demands increase significantly. And since vectors need to be stored in fast and therefore more expensive storage, such as RAM, for low latency searches, as the size of our dataset grows, so does the cost of storing and maintaining our data. Quantization offers a solution by compressing vectors to smaller memory sizes, making the process more efficient. There are many ways in which you can quantize your vectors, and here in this video, we're going to talk about the 3 main ones: scalar quantization, binary quantization, and also product quantization. Let's start by explaining how scalar quantization works, because it's one of the most simple and effective, really, quantization methods that you can use if you're looking for just a bump in speed without losing a lot of precision. Right, so to understand scalar quantization, let's understand how Qdrant represents our vectors, right? So in Qdrant, each dimension is represented by a float 32 value, which basically uses 4 bytes of memory. Now, when we are using scalar quantization, we map our vectors to a range that the smaller int8 type can represent. An int8 is only 1 byte and can only represent 256 values, ranging from -128 to 127, or from 0 to 255. This results in a 75% reduction in memory. For example, if the dimensions of our vectors lie in a range of -1 to 1, then scalar quantization will transform these values to one of the ranges that it can represent. For example, it will create a new representation that fits within the range of -128 to 127. So when we are compressing using scalar quantization, the system maps the float 32 values into this new range. This is a great choice if you're just looking for a quick boost in search speed without affecting accuracy too much. And it also slightly improves performance because calculating distance metrics with int8 is faster and more performant than with float 32. Even though scalar quantization might not match the same memory compression and performance gains of binary quantization, which we'll cover next, it's still an excellent default choice when binary quantization is not fit for your use case. Now, let's see when that happens and everything that you can do with binary quantization. Now let's get into binary quantization, which is an excellent option if you're looking to reduce memory usage while also achieving a significant, and I do mean 40x significant boost in speed. This is one of our favorites to work with, and definitely one that we recommend you to test because of the absolute performance gains that you can gain with this compression method. So the way binary quantization works is by converting high-dimensional vectors into simple binary representations, 0 or 1. Values greater than 0 are converted to 1, and values less or equal to 0 are converted to 0. So let's go back to our initial example of a 1,536-dimensional vectors that require 6 kilobytes of memory, which is 4 bytes for each float 32 value. After binary quantization, each dimension is reduced to 1 bit, which is 1/8 of a byte. So the memory required now is 192 bytes. Now, this is a memory reduction of 32 times. So binary quantization is by far the quantization method that provides the most significant processing speed boost without losing too much accuracy. So definitely binary quantization can provide a huge performance gain, and it can speed up search speed by up to 40 times depending on the dataset and hardware. So you're not only compressing the vectors by 32 times, you're also improving search speed by 40 times, when you use binary quantization. However, not every model is equally compatible with binary quantization. You can see some models experience a greater loss in accuracy when are quantized with binary quantization than others, and some models perform really well with binary quantization. So the general recommendation is that you use it with models that have at least 1024 dimensions to minimize the accuracy loss that can come with it. So these are some of the best models to use binary quantization with. Finally, product quantization, which is a quantization method that we don't usually recommend due to the high accuracy loss that comes with it. However, it's great for you to understand how it works and if it might possibly fit your use case. Now, product quantization is a method used to compress high-dimensional vectors by representing them with a smaller set of what we call representative points. The process begins by splitting the original high-dimensional vector into smaller subvectors, and each subvector represents a segment of the original vector. In this way, we can capture different characteristics of our data. So for each subvector, a separate code book is created, representing regions in the data space where common patterns happen. So each region in the codebook is defined by a centroid, which serves as a representative point, summarizing the characteristics of that region. Depending on your configurations, you can choose to use product quantization to compress your vectors by 4, 16, 32, or even 64 times. However, these high compression configurations can lead to a very significant drop in quality when we compare this method to scalar or binary quantization. In this table, there is a quick comparison of the three methods, so you can have a look and understand which one is best for your use case or for your type of data. One thing that is important to note here is that Qdrant will always maintain the original uncompressed vectors in your collection. This means that you can safely experiment switching quantization models, adjusting configurations, or even removing quantization entirely without needing to re-upload your vector data. Each method comes with its own trade-offs between memory savings, computational speed, and also accuracy. And remember that when you enable quantization, both the original and the quantized vectors are stored in RAM by default. You can move the original vectors to disk to significantly reduce RAM usage and lower system costs by setting the parameter on disk to true. This will move the original vectors to disk while keeping the quantized vectors on RAM, which are the ones that you need to perform a fast search. Without explicitly setting on disk to true, you won't see any RAM savings, even if you're using quantization. So make sure to configure both your storage and quantization options based on your memory and performance needs.